Current to excite the field windings can be supplied from an external source. In that case, the generator is classified as separately excited. A small part of the generator's own output can also do the exciting. In that case, it will be a self-excited generator. Self-excited generators must be initially magnetized. The residual magnetism in the core of the field winding provides enough magnetism to begin generator action. The field coil winding may be connected in several ways. This is a series wound generator, which means the field coil is in series with the armature. Because of this series arrangement, it has poor voltage regulation. The reason for this can be demonstrated in the following manner. Additional load will cause more current to flow in the field coil. Increase in field strength increases voltage. Increase in voltage causes more current to flow. This continuing action stops only when the core is saturated. When instead of in series, the field winding is connected in parallel with the armature and the load, we have a shunt wound generator. Now the field current is independent of the load current. Therefore, an increase in armature current will not cause an increase in the voltage output. Voltage regulation here is greatly improved. By changing the armature winding, a compound wound generator results, which combines the best features of both types, the series and the shunt wound generator. When windings are arranged so that magnetic fields oppose each other, it becomes in effect a series generator. This is used only where constant current is the prime requirement, such as in arc welding. By changing the magnetic polarity of one of the fields, the field windings aid one another. As a result, this compound wound generator has good voltage and fair current regulation. A graphic representation of generator output characteristics with terminal voltage plotted vertically and armature current horizontally would look something like this. As we have seen, in the output of the series wound generator, voltage regulation is very poor. In parallel or shunt wound generators, the voltage regulation is fairly good, but current regulation is poor. Compound wound generators offer a flat compounded output that is normally most desirable. It combines the good features of both the shunt and series wound generators and provides stable voltage output under changing loads. To see what really happens, let's go to a drawing again. Here, a conductor is suspended in a magnetic field. Current flow from a power source creates its own magnetic field in and around the conductor. This field around the conductor reacts with a main magnetic field to cause motion of the conductor either out of the field or into it. The arrow point indicates the direction of the current flow in the conductor. In this case, the flow is toward us. The field of the conductor has the same direction as the main field above the conductor and the opposite direction of the field below the conductor. These two magnetic forces added together distort the lines of the main field upward. The field above the conductor is thus made stronger and the field below the conductor is made weaker. So the conductor moves down. Conversely, when current flows in the opposite direction, that is to say, away from us, the field of the conductor opposes the main field above the conductor. This aids the main field below the conductor, distorting the lines down. The field below the conductor is thus made stronger, while the field above the conductor is made relatively weaker. This forces the conductor to move up. With this basic principle of motor action understood, we can now examine the DC motor. The basic DC motor, like the DC generator, consists of a pair of magnetic poles, an armature made up of a single turn loop, a commutator, and a brush assembly. As we have seen, a conductor in a magnetic field will move when a voltage is applied to it. With the voltage applied and the magnetic field and current flow as shown, the right conductor will be pushed down, while the left one is pushed up. Since the forces on each conductor are now in exact balance, there will be no more motion. Adding another loop and two commutator segments ensures that at no time will balancing forces cancel each other out. With this setup, there will be motion at all times. As one commutator segment is moved away from the brushes, another now takes its place and the movement continues. The greater the number of loops in the armature, the smoother its motion. For this reason, rotors in practical DC motors have many loops. Since current in the rotor loops must reverse each half cycle, two commutator segments per loop are required. Here in the motor, as in the DC generator, there is a neutral plane. The interaction of the conductor fields on the main field causes this neutral plane to shift and sparking to occur when a load is added. Sparking in DC motors also produces burned commutators and interference in nearby electronic equipment. This sparking can be prevented in one of two ways. One is by the adjustment of the brush position. The brushes are moved until they lie in the adjusted neutral plane. In the motor, as in the generator, small interpoles between the poles of the main magnets are also used to eliminate the shift of the neutral plane. These interpole fields tend to oppose the fields created by armature reaction. The neutral plane is moved back toward its correct position. Also aiding are compensating windings, which carry armature current in the opposite direction to the current in the armature conductors. The neutral plane is thus maintained in its proper position. DC motors operate most efficiently when sparking is eliminated. We saw earlier that when a conductor is moved by mechanical energy in a magnetic field, an EMF is generated. This is generator action. In the DC motor, when rotation is desired, it is necessary to apply an EMF to the conductor. However, when used as a motor, an opposing EMF is also generated in the conductor. This is called the counter-electromotive force, or CEMF. By Lenz's law, the generated CEMF must oppose the applied EMF. The amount of CEMF depends on the speed of rotation. This is of practical importance in large motors.